Good morning, everyone. Today we have a different schedule in algorithms and data structures, as I informed you before, because we have this open day on campus as of 11 a.m. So the lab rooms are already taken as of 8. So we're doing a lecture today from 8 to 11. Last week, we started discussing trees and we looked into binary trees and how to traverse trees. So we saw what a tree is. It's a recursive data structure. We have a top node that is called the root, and the root may have multiple children. And each child has exactly one parent node. The root has no parent, that's the exception. All the other nodes have parents. And you've seen trees in lots of examples before. You can use this, for example, for an organizational chart, but also for file directories, inheritance hierarchies. Trees are also used as a foundation for database systems and so forth. We looked at the abstract data type of trees, and then we looked at binary trees, which are probably some of the most common trees, where every node has two children at the most, a left and a right child. And we saw we can use such binary trees, for example, to express mathematical terms. But then we also saw how we can implement this. And we have a node class, and a node has data, the entry of the node, as well as a left and a right child. And we saw we can insert data, making sure the data we're adding is actually sorted. So we discussed that procedure. We also discussed how we can find a value in a tree. And then we discussed traversing, and traversing allows us going through the tree, visiting each node in the tree exactly once. And we saw different traversal algorithms in order, pre-order, and post-order, as well as level order. So what is traversing needed for? If we want to visit all the elements in a tree exactly once, we need one of these algorithms. It depends on your use case, which one you would pick, or maybe amend them to do something specific that you wish. One simple example could be you have a binary tree that contains integer values and you just want to sum up all the values. This is something you do quite easy. For example, if in order, pre-order, post-order, or level order, here it wouldn't make much of a difference. If you have some other examples like this one here, maybe a level order is not very helpful to evaluate these expressions, but it depends on your use case. We studied those four traversal algorithms in detail. We also added some elements, and then we implemented the in order. We could implement it as a very simple print method, but what we actually wanted was a generator. So with a generator, we would always get through an iterator the next entry. This would allow us to get quickly the first element, quickly the second element without pre-computing all of this, which may even not be feasible if the tree is infinitely large. So with a generator, we always generate the next element, and with an iterator, we run the iterator on a generator. And we also saw we can have multiple iterators on one generator and so forth. The concept of iteration and generation not only applies to trees, but lots of other data structures. And we actually saw we had dealt with this many times before, for example, through using a range. Then the last example we looked at was inverting a tree, which looks surprisingly simple, but it isn't that simple to a lot of people. It turns out you're probably prepared the best applying for a job at Google after you finish your second or third semester, when you still know the foundations of algorithms very well. And as you progress with more advanced lectures, you may forget some of these foundations, but Google seems to care a lot about the foundations when you apply there. So if you want to apply for a job at Google, maybe for an internship, you can do this, or you can try this sometime soon. This is what we started last week, and today we will continue with trees. We will look at more advanced trees, and after that, we will also look at decision trees and how to learn decision trees. Now, remember our binary trees from last week. We said we wanted to store the data in a sorted way. So we have something like this. So we have a binary tree. Imagine I want to add the following values. I'm starting with a 5. So the 5 would be the root. Now I'm adding a 3, which would be the left child. If I want to add a 10, it would be the right child of the root. And if I add now a 4, it would be the right child of the child. So this would be the 4. And if I add, say, a 20, it would be the right child of the right child. And if I add, say, a 9, the 9 would come here. And this looks okay, but now imagine we want to do something different. Say we want to add the sequence of 1 to 8. So add 1, 2, 3, 4, 5, 6, 7, 8. So I'm adding them in exactly that sequence. So I'm adding a 1 as a root. Then the 2 is the right child of 1. Now I'm adding a 3, which is the right child of the 3. I'm adding a 4, which is the right child of the 3, and so forth. This is a tree, but it is a tree that is sometimes called in the literature a degenerated tree. One can argue if the word degenerated is very helpful or not. But what we are creating here is actually a tree that more looks like a list, because I'm always just appending an element to the right of the rightmost child. So what I'm adding here is technically a tree, but more looks like a list. But if we keep doing this, adding and searching in the tree will be extremely slow, because what I have is just a list. I don't have a tree, which is a far more advanced data structure. So a tree should not look degenerated. Rather, a tree should look like this, where you have a root. Ideally, you have a left and right child, and each of these children has left and right children as well. This is something we would call a balanced search tree. So we're now not just talking about trees, but we are talking about search trees. What are search trees? Our goal is that we store data efficiently in a tree so we can search efficiently in a tree. Imagine I have a balanced search tree. Tree can maybe look like this. We have a 10 in the root, then a 20 as the right child, and a 5 as the left child, and then a 1 here, and a 6 there, and maybe here a 15, and here a 25. Now, if I want to search for a value in a balanced search tree would mean that I have more or less the same elements in the left and right recursively. It's not always perfectly balanced. Imagine I wouldn't have the 25 in here, for example, but then the tree would be almost balanced, but still I have more or less the same element, the same number of elements in the left and right. But now imagine this tree is perfectly balanced and I'm looking for a value. So I have n elements. What do you think searching would be? If I want to search if a value is in the tree or not, this would be O of what? If you have any guesses, send this to the chat. What do you think the complexity of the search in a balanced search tree would be? If you think you have a guess, maybe send me some positive reaction, then I'll wait for you to add this in the chat. So maybe green sticker would mean you see what the complexity could be, or red if you don't see it. And if there's just no one seeing it, I'll be happy to show this. So the only negative reactions. So if I have a perfectly, or if I have a balanced search tree, then searching in the search tree for an element when I have n elements, then this would be O of log n. Concretely, it's the binary logarithm, but we don't care about the base of the logarithm because this is something you can compare a bit to the binary search, because say if I search element 7 now, if I search 7, I'm checking the root and the root is 10. It's not 7, but 7 is less than the root. So I only need to look into this half here. Then I'm checking the 5, which is not the 7, but I know I must only look into the right subtree again, and so forth. So this works a bit like the binary search. In fact, binary search works, say, on a sorted list. And if you do a search in a balanced search tree, then it's the same complexity. It's O of log n. You can also think about the recurrence relation if you wish. The recurrence relation is the same as the recurrence relation of binary search, so it has the same solution. It's O of log n, because in each step I'm checking the node, and if the node is the value that I'm looking for, I'm done. If it's not, I just explore yet another half of the tree I have just, or of the subtree I have just looked at. So each time I'm looking into half of the space I've looked into before. So I keep halving, and in the worst case, I need to go down to the leaves and then I'm done. But this is really the worst case, but in the worst case, I need to go down log 2 of n many levels. So the complexity of this is O of log n. For a balanced search tree, so where the elements are well spread out to the left and right, what would be the complexity of the search of a degenerated tree that is not balanced? What do you think the complexity would be here? O of what? If you see it, maybe send it to the chat or send a reaction, green or red, if you have a clue what a complexity of the search in a degenerated search tree could be. We got the right answer. It's O of n in the chat. Because in the worst case, I really have to go down to the very end here, and I have to look into all n elements, because each entry, the root has only one child, this next child, or the child has only one more child, and so forth. So in the worst case, if I'm looking for a value, I really have to go down to the very end of the tree, and that means I need to look into n elements. So this would be O of n. That's why we really prefer these balanced search trees. Now we're wondering, how do they work? In the literature, there's a huge number of balanced search trees that have been described. Very simple ones like this binary balanced search tree that I've just visualized, but there are far more complex trees that you find in the literature. AVL trees, red-black trees, B trees, or so-called 2-3-4 or simply 2-4 trees. What they could look like is a 2-3-4 tree not only has a left and right child, but it can have multiple children, up to 4 children. And I can store in a node multiple values, for example, 1, 2, 3. And say I have a value here, number 3. And then everything down here is greater than K3, but less than H2. So I have 4 children, and I'm dividing the space of the values with up to 3 values in the node. And what can happen is, if I keep adding elements in a tree, the tree may not be balanced anymore. And there are some thresholds where the tree is maybe not perfectly balanced anymore, but if you keep adding more and more elements, we want to make sure it does not degenerate. So what it does is sometimes it breaks up some nodes, it moves some elements around, always with the goal of having a balanced search tree so we can search efficiently. When we look at our binary search tree from before, that one often uses a concept of a rotation. If I have something like this, which looks degenerated, where I'm just growing to the right and it becomes more and more imbalanced over time, I can do so-called rotations. And then A is not the root anymore, but actually B becomes the root by doing a rotation. So I'm rotating around B, and then B becomes the root. C becomes the right subtree of B, and A becomes the left subtree of B. And applying this concept of rotations, the tree over time, and the rotation also needs to be done recursively, the tree becomes balanced, and then I can search in it efficiently. The so-called 2-3-4 trees or 2-4 trees are a different approach where I can even store multiple values in a node, and I can break up nodes, I can move subtrees around, and also sometimes uses something that is a bit like a rotation. So that's one concept. The literature also describes so-called red-black trees. And another very popular type of tree is a B tree, an even more advanced data structure. And these B trees can also have multiple values in their nodes, and we have subtrees in the B tree. And eventually, what all of these trees have in common is if I keep adding elements, they need to do something by moving nodes around, subtrees around, rebalancing, always with the goal of having a more or less balanced tree. But some of the more complex ones, like a 2-4 tree or a B tree, that they not only have a left and right child, but actually sometimes more than two children and more than one node, more than one entry in a node. What you would see in a typical algorithms and data structures course, like most of the other algorithms and data structures courses taught around the world, this is a topic that is discussed for maybe 1 or 2 weeks. But our course is not a typical course, so we're doing something a bit different. We're not discussing the balanced search trees here in detail in this course because most of the students taking this course are from one of our AI programs. I know we also have some cybersecurity students here, but they also need AI. And what I think is a lot of students who study algorithms and data structures then study in detail these balanced search trees, but a lot of that looks like it's made up just like self-purpose, just an end in its own, like just, yet another type of tree, but you don't really see what you would need trees in reality for. So we will instead spend today on doing something that is closer to AI, and we will actually learn decision trees. Because most of you, when you work in industry as AI experts or cybersecurity experts, you need to know about trees and concrete applications, but probably you will not be implementing balanced search trees on your own, and you'll just be using a library to do this. That's why I just wanted to show you the essence and the idea of what balanced search trees are about. If you want to study them in greater detail, there is a great video on YouTube that shows, for example, how B trees work. You're welcome to watch the video. I will not quiz you in the exam on these videos. The Goodrich book also provides a lot of further reading and explains these balanced search trees in detail. If you wish, read it. In the exam, I will not quiz you on these two further readings. I would only quiz you about what we have just discussed, because I want to show you some concrete applications of trees now, which is decision tree learning. But feel free to read this and get a better understanding. These B trees, in fact, they are actually the foundation of modern database systems. So if you have relational database systems like Postgres or from Oracle, internally the database management system is using something like a B tree, a bit more advanced, to store your data efficiently, and this will allow you also to query your data efficiently. So if you want to learn more about this, watch the video or look into the Goodrich book. But we will now look in this course into decision trees. So what are decision trees about? Decision trees help us to make a decision based on various inputs. Concretely, a decision tree could look something like this. Say we have two variables, A and B, and we start looking into A, and if A is no, we are returning value 2. If A is yes, then we still need to look into B. If B is yes, I'm returning 1. If B is no, I'm returning a 2. In fact, if you see number 1 as true, number 2 as false, this would just be the AND decision tree because A and B both need to be yes in order to come to true, otherwise it's false. You could also have the OR decision tree where if A is yes, we are done, we are returning true, which is 1. If A is no, I'm still looking into B. If B is also no, I'm returning 2, which is a false. However, if B is yes, then I'm returning 1, which is true. And such decision trees is something that we use actually quite often as a set of rules to make decisions. You could also implement more complicated, more complex decision trees in a computer. For example, for a video game where you have an AI as a bot, and you could check, for example, if the enemy is visible. If the enemy is visible, then we're checking if the enemy is less than 10 meters away. If that's the case, our bot would attack. If the enemy is further away, we would still check some other variable. If the enemy is on flank, if not, we would attack. If yes, we would move. However, if the enemy is not visible, we would do some other checks. And eventually, these leaves are our decisions. So this is how we would determine what the AI bot in the game would do: creep, attack, or move based on various variables. You can also see such a decision tree just as a set of rules, in fact. And now the question is, how do we come up with a decision tree? Say we have some decision problem, we could manually draft a decision tree, and you know now how to implement a tree using the methodology from last week, where we have nodes and they have different children, and we know how we can traverse a tree. And here we would actually then not try to traverse by printing out the next element, but rather we would go further down in the tree based on what we are checking in the node, and based on the result, yes or no, we would go further down the tree up to the leaf in order to make decisions. So this is one thing that we manually draft the tree based on different rules that we are trying to come up with. Today, we will discuss not how to implement something like this, but rather how to find a near optimal tree. So we want, in fact, from various examples of how to decide, we want a decision tree that is as small as possible, yet does what we want from the data. And that's decision tree learning, and that's the focus of today's lecture. I want to introduce a little bit more terminology now. So what we want is actually a classification tree, because what we have are different inputs. So we have various variables, like is the enemy visible, is the enemy audible, is the enemy far away, or whatever. These are the variables, and based on the variable values, we make decisions. So, or we are classifying the problem into the action that we would take. And this is a so-called binary decision tree, because each node has up to 2 children, and binary means here the structure of the tree, but we have more than 2 different classes into which we can classify. Concretely, we have 3 classes, which is creeping, attacking, or moving. So we have up to 3, we have 3 classes into which we can classify our instance into. What we have is concretely, when it comes to classification, our output is discrete. Discrete means we have a fixed number of possible outputs: creeping, attacking, or moving. So it's three, or it's when we classify our instance, we would get one of those fixed possible outcomes. And that's a classification tree. There are, however, also trees that we don't use for classification, but for regression. So regression would be a continuous value. For example, if you want to predict a monetary value, say you have an instance and you want to determine how much it's worth. Say we want to do housing price regression. A house has multiple parameters or multiple variables, say the size of the house, the number of the rooms, the condition the house is into, and we want to eventually turn that into a concrete monetary value. We would not be using classification because classification would be just discrete values, so a fixed number of possible outputs. However, with a continuous value, we're doing a regression. Say that's, for example, a monetary value. In the input values, we have seen so far a Boolean because we've always seen yes or no. These are the input values, but you could also have numeric input values. So based, for example, if a value is in a certain range or greater than a range or less than some other value, this could be a numeric value given a range, and we could, based on the value, we could make some decisions. Sometimes there are also set input values that we have maybe one of a given set of values, but that's not too important for now. Today, we will focus on classification trees and we will deal with binary input values. And I'll show you now what we want to do. Why are decision trees so interesting? Decision trees are one of the simplest, or decision tree learning is one of the simplest machine learning algorithms possible. So it's a good intro to machine learning now. So you'll have an early start into AI and you will see a concrete application of trees that we have studied last week and today again. And you'll be able to turn this into a concrete machine learning algorithm, also as part of the coursework, but I'll talk about the coursework later. Decision trees look simple. However, they are very fast to evaluate. And in fact, they are actually a quite powerful machine learning algorithm, even though they initially seem simple, but they are simple to implement. Yet you can use them to solve a lot of complex problems. I know that many of you hear about neural networks all the time. Neural networks are interesting and helpful for certain problems, but neural networks are not a silver bullet. And obviously, there are still hundreds of different machine learning algorithms, and so are decision trees. Quite helpful for a lot of problems. And the good thing is we can train them quickly, we can evaluate them quickly. With a neural network, all of this is way more complex. Now, our goal is, I will soon show you a data set, and we have a data set here, and we have three input values per example. So the way you need to read this is we have rows and we have 12 rows, and these are examples. So we have 12 examples, and for each example, we have in each of these three attributes, we have a value. Say the first attribute is enemy visible, the second one is enemy distance, and the third one is enemy armed. And what we see here is we have the enemy visible, it's either 0 or 1. Enemy armed is either 0 or 1 as well. And enemy distance is not binary, it's actually one of three possible values. The first possible value is less than 10. The next one is 10 to 20. And the last one is greater than 20. So we have three possible values in the enemy distance attribute. And these are the three inputs. So the three attributes are the input. And we have a concrete label that is attached to the example, which is called attack. And attack is true or false. So what we want to build is a decision tree for our game AI that based on enemy visible, enemy distance, and enemy armed, our AI should determine whether it should attack or not. And we have 12 examples here of how the AI should decide. And what we could do is now, we as humans, we could try to come up with a decision tree from the data. But we also want we also want a decision tree that is relatively compact. So we don't want a huge decision tree coming up with a lot of rules to realize this, but rather a compact, small decision tree to do that. Now, we could hope to find the smallest decision tree possible, which would be the optimal decision tree. But it turns out, assuming now our attributes are binary, so enemy distance is actually not binary because it has one of three possible values. But assuming that we have our attributes and they are all binary and we have n many examples, and I want to find the optimal decision tree, so the most compact, the smallest decision trees for n examples, I would need to evaluate 2 to the power of 2 to the power of n many possible trees. So even if n is just 10, this would mean 2 to the n, which would be 1024, and then 2 to the power of 1024. So we are not really able to assess this. This is so-called NP complete problem. Did you study this in your intro to computer science, NP completeness? Has anyone ever heard about NP completeness? Maybe green reaction or red reaction, if this is something that you have discussed in your intro to computer science in your first semester. I'll wait for your response. So I'm still waiting for responses. So I got a red response, meaning this was not discussed, so it will probably follow later in your studies. So NP complete are extremely challenging computational problems. I'm not providing a detailed intro to this now, but in order finding the optimal decision tree is a so-called NP complete problem. And even if n is small, you would have an infeasible amount of possible trees to look into in order to find the optimal tree. And we want a very compact tree now. We don't want a super big tree for this, but a compact one. But we have 12 examples, and this one here is, this attribute is even not binary. So we see even plugging 12 into here, this will not work. So what we need is a heuristics in order to find an approximate solution of a small tree. Maybe not the smallest tree, but a relatively small tree, so an approximate solution to our computational problem. And for this, we will now study an algorithm that is called the ID3 algorithm. And the ID3 algorithm uses a concept that is called entropy or entropy theory, something that comes from information theory. And this will help us to build a compact tree. The algorithm uses a divide and conquer strategy. Divide and conquer is something we have discussed a few weeks ago because we have this data set and we don't know how to find the decision tree for the data set. But maybe we can split the problem into smaller problems, then solve the small problems and then put it all together. And what we do is we want to find the most important attribute. So we have three attributes and we want to find out which one is the most important one. And the most important one will be put into the root. So we will use the root to make the best split possible. And then we still have maybe subtrees, but we will try to split as much as possible in the root. And for the subtrees, we will use from the attributes left, the next one that is still most informative. So we are not just building a so-called divide and conquer algorithm, but we are building a greedy divide and conquer algorithm. So there's also a class of algorithms that we call greedy algorithms. And greedy means in each step, take as much as possible. And here we actually want to start with the most important attribute and then split this into subproblems that we still keep solving. But we want to split, or we want to take the attribute that is most important. So this is a greedy divide and conquer algorithm. And we split this into smaller subproblems. This is the algorithm. I will explain you now how, I will discuss how the algorithm works. It's in pseudocode, and then we will apply it to our data set. We will do the calculations together. So what we see is our algorithm is called decision tree learning. And I'm not implementing decision tree learning here for you because this is one of the coursework problems, but I'll mention this later once we have finished this. So we have an algorithm that is called decision tree learning. And we see it's a recursive algorithm because decision tree learning will call itself. And we will later see the recursion. The decision tree learning algorithm has three parameters. It has the examples. So from our table that we saw before of the training data, we have the examples and we have the attributes, which are the columns. And we also need the parent examples, but we will see this later. It doesn't matter for now. What we can check is now a few corner cases. Imagine all the examples have the same label. So we go back to the data set. Imagine if all the examples here had the same label. Either all are true or all are false. Then I don't need to build a decision tree. Then I'm done because there's nothing to decide about. So if all the examples have the same classification, I'm just returning that label, that class. This is something that would hardly appear on your whole data set, but since it's recursive, this will happen sooner or later, and then the training will be aborted. We'll see this later. It could also happen that the list of examples becomes empty through the recursive calls, or that the list of attributes becomes empty. If that's the case, then we need another helper function, which is called plurality value. And we pass examples to plurality value, or you can just say majority value. What this means is I have my examples and I'm unable to further split them because, for example, I run out of attributes. And here I would pass examples and they may not all have the same class, but I would just return the majority class. And I say, for example, I have 10 examples in here, 8 are of one class and 2 are from another class. Then I would just return the majority class. These are a few corner cases. They mainly appear through the recursive calls. Now, if none of these cases applies, and we will see them later in the example, then the actual interesting part of this algorithm is appearing. What I need is an importance function. And the importance function, what I can pass is, I can pass one of the attributes, so one of the three columns, and my examples, and I want to find out how important is that attribute, so that column, for the examples. Because what I told you is we want to find the most important attribute and start splitting based from there. So what I could see is, say from my data set, I have these 12 examples. I could try to calculate how important is this attribute in order to split my data set. How important is this attribute in order to split the examples? And how important is this attribute? We will later see how to calculate the importance. And once I'm able to calculate, I can see, well, this has a certain importance, this has a certain importance, and this has a certain importance. And then I want to pick the most important attribute. In pseudocode, I'm using a notation that is called argmax. Who of you has seen argmax before? Green or red reaction. This is an operator. No one has seen it. I assume this. Has any one of you seen a max operator so far in your studies? If you have seen a max operator, maybe green reaction, or still red if you have never seen a max operator. One has seen it, and that's fine, and the others have not. So we will quickly study this on the whiteboard, and we will see what the max operator and what the argmax operator are. So we will now look at max and argmax. So we are starting with a function, and the function is called f of a, and we can say it's a piecewise defined function. It returns 1, 2, 3, or 4. It returns 1 where a is 10, a 2 where a is 5, a 3 where a is 1, and a 4 where a is 7. So a can be values 1, 5, 7, and 10, and the function returns 1, 2, 3, or 4. Now, we will start with the max operator, where max is the simpler one. I want to know what's the max of f of a. So I'm allowed to pass values 1, 5, 7, and 10 into f. And I want to maximize the value of f. So I want to maximize the output value of f. So max of f of a. What's that? What's the maximum value that f can return to me? Send it to the chat, please. If you still waiting for the chat. So one person says the maximum value that f can return is 10. Are you sure about this? I'm not caring about the maximum input value. I'm caring about what the function returns. So what's the maximum value that the function can return? Maybe rethink it and send it to the chat. 4. The maximum value that f can return is a 4. Now we are coming to argmax of f of a. And argmax means the following. I want to maximize the output of f, which is the maximum value is 4, but I want to know which argument value, meaning which input value, would maximize f of a. And I get the maximum of f when I put in a equals 7. So the argmax of f of a is 7, because the max is 4 and the input value to maximize the function is the argmax, and that's 7. So argmax does not mean what's the maximum input value. The maximum input value is 10, but this is not meant by argmax. Argmax means which argument value or which input value maximizes the function, and that's 7. Maybe just confirm with a green sticker that the difference of max and argmax is something you've understood now. So, seems clear. So, Not that difficult, in fact. Now I have this statement here, argmax, and I'm argmaxing the importance function. So importance function gives me some numeric value for some attribute and all the examples. Examples comes from here. And now I need to put in one attribute into and all the examples into importance. Then the next attribute. So I need to try out all the attributes I still have left. And this is what argmax does for me. And we see argmax has something down here. What I determine or what I define here are the possible values for A. And A is an element from the set of attributes. So attributes is in fact a set. And this means I'm going through all the attributes. I'm picking the first attribute, say the order doesn't matter, but the first from the set, which is my first A. I'm passing this into the importance function, and I'm trying to maximize the importance function. Then I'm picking the next attribute, and I'm doing this again. Eventually, I'm trying this for all the possible attributes, and each time I will get an importance value. And I don't care about the importance value. That's why there's not a max, but an argmax. But I'm caring about which attribute maximizes the importance function. And that's the attribute I'm caring about because I want to continue with this one. I don't care about the importance value. I just care about which attribute maximizes this. This is the most important one. And I'm assigning that one to capital A. Maybe just confirm if you've understood this, what this line here means. Green or red, because it's a very important line that we will need when we apply the algorithm. So send me green or red reaction. So I got more red reaction than green reaction. So maybe please tell us what you would like to have explained again, what has not made sense to you yet, because then I'm able to help. Maybe turn on your mic or set ideally your mic because probably asking this. So one person asked me to go over it again. So I'll do it once more. So we have the importance function, which calculates how important some attribute for the examples is, because we want to find the attribute that helps us to split the data set the best. And I'm trying out all the possible attributes because I have a set of attributes. I'm trying this for the first attribute and the second attribute, so all the possible attributes. And one of them will maximize the importance function. So I will get for one of these attributes a maximum value. I don't care about the maximum value, but I care about the attribute that has maximized this. So that's why argmax. The attribute that has maximized this term. And that attribute, just from our data set before, is one of the three columns in this example. It's either enemy visible, enemy distance, or enemy armed. And this is the one I'm storing now in capital A. Hope you got it now. If not, you will be tasked also with implementing the algorithm, but now I'm getting green reactions, so it seems to make sense. What I have now is I'm creating a new decision tree where the root is A. So A is the attribute that will be put in the root in order to determine or in which I'm doing a test. And the test would then be, is, for example, the enemy visible 0 or 1? If it's 0 or 1, I will continue with more checks in the decision tree, but we'll start building the decision tree. So you will see this later. Now, I have something like this. What does that mean? It's a loop where I go through values vk in A. I'll show you this. A is one of the columns. And in this column, for example, enemy visible, I have possible values 0 and 1. In enemy armed, I also have two distinct values, 0 and 1. In enemy distance, I have three distinct values, less than 10, 10 than 20, or sorry, 10 to 20, or greater than 20. So what I'm doing here is I'm going through the distinct values in A. And then I'm building a subset of the elements with that distinct value. We've discussed sets a lot in this course. Concretely, when we looked into graphs, when we studied graphs, we've seen expressions like this. What I want to do is I want to go through all the examples, which is the attribute here, the parameter here. I go through all the examples, and for each example, where the attribute A, so our attribute A here, is that distinct value that I'm currently looking into the loop. I'm building a subset. I'll show you this on the data set here is, imagine I pick as the attribute enemy visible. And I have two distinct values, 0 and 1. And now I'm splitting this into a subset. The first subset would be this one here, because the first distinct value in enemy visible is 0, and I'm taking all the rows where the value of the attribute is the first distinct value. So all of these are 0, and here all of them are 1. If I had enemy distance and I split on that, one distinct value could be less than 10. So this would be rows 1 and 2, and rows 7 and 8, and so forth. So I look at all the rows for which that attribute has the distinct value that I'm exploring. And this is a subset. And I'm doing this loop for all the distinct values. So in each iteration, I'm building a subset. And then comes the interesting part. I'm doing a recursive call. I'm calling decision tree learning recursively, and I'm passing this subset of examples to the decision tree learning algorithm, so EXS, and I'm passing all the attributes except the attribute I have just looked at. So what this notation here means is I'm doing a different set. Attributes is a set, and I'm removing A from it, because I'm building now a decision tree, and I have put, say, enemy visible in the root. And in that tree, once I have picked an element as the root, in the subtree under that root, I don't want to look into that attribute again, because I have already explored it. I only need the remaining attributes to be explored. And this is exactly what this notation here means. Attributes and removing the attribute I've just looked at. We also have these parents examples, and parents examples are just the current examples I have looked at in here. And this, so the old examples is then passed as the parent examples. And parent examples, as I said, are maybe needed in some exceptional circumstances. Say if I run out of examples or something, but this is rare cases that may be happening. It's not too important now. And even if I just need the plurality value, so the majority value of that set of rows. Now, when I call this recursively, eventually, when this is done, it will return me something. We will later see what decision tree learning returns. In fact, it's returning the tree I have just started building here. And when the recursion finishes, a subtree will be returned. And I'm adding that subtree to my current tree that I have built here, where I'm doing that root test on A. And I'm adding essentially a branch to my current tree, where A is that current distinct value I'm looking at, and I'm putting the subtree there. We will play through this with the data set very soon and we will run the algorithm together step by step. So I know this is not an easy algorithm, but I like the algorithm because like this, you can have an introduction to machine learning because we are learning a decision tree from data, and we have a concrete application of trees, and we also actually see recursion, which is something we have been studying in this course for quite a while now. The only question left is the following. How do I calculate the importance? Because we said somehow we can measure how important an attribute is for the examples in order to split them. Now we need to see how we can calculate importance. For the importance function, we will use a concept called information gain, which comes from entropy theory, which is a fundamental quantity in information theory. Has any of you ever seen the entropy? Some formula like this. If you have seen it, green reaction, or red if you have not seen it. So some have seen it. Maybe you can tell us where you have seen the entropy before. Be curious. Either turn on your mic or tell us in the chat. Some have not seen it, while others have seen it. So one has seen it in Foundations of Computer Science. But since that course is taught by different professors based on your degree program, maybe one has taught it and someone else has not taught it. We will now explore this concept together. So, entropy. I will first write down the formula for the entropy, and then we will study it together. So the entropy is often denoted H of a variable V is minus the sum. We go through the elements in the variable. So there may be 2 or 3 or how many values in the variable. We want to know what's the probability of that value Vk times the binary logarithm of the probability of V of k. And I think the screen share somehow just terminated, right? Maybe just confirm because I don't see it on the other screen anymore. So screen share is back. So, and what I'm doing is I'm multiplying the probability of the value Vk, multiplying it with the binary logarithm of that probability. And I'm summing this together for all the values in the variable, and I'm taking the negative of that sum. The unit of the entropy is called bit, but these bits are different bits than you know from binary computing, but this here comes from information theory. So what does the entropy do? It's a measure of the randomness in a variable. So it allows us to determine how random a variable is. And later we will extend that concept, and this can help us to calculate the importance of an attribute. So we look at an example. It's a fair coin. A fair coin that has heads and tails where heads and tails has each a chance of 50%. So I flipped a coin, it's a fair coin. And we can try to calculate this. So heads is 50% and tails is 50%. We can try to calculate this. So we can say H is minus. And now we have two values in the variable heads and tails. So we can say the probability of heads is 50%. So, well, I write it down step by step. P of heads times the binary logarithm of P of heads plus the probability of tails times the binary logarithm of P of tails. Now, this is 50% and this is 50%. So we can try to plug this in. We can say 0.5 times the binary logarithm of 0.5 plus for heads 0.5 plus the binary logarithm of 0.5. We can try to simplify this. So here it's 0.5 and 0.5. So it's just 1 times the binary logarithm of 0.5. And if you remember binary logarithms well, remember the binary logarithm of 0.5 is the binary logarithm of a half. And this would mean we have the logarithm of a half divided by the logarithm of 2, because this is the binary logarithm. Well, I'll just give me a second. I'll write this better. So this 2 here. And if you keep simplifying this, eventually this will give you 1 bit. But then you should all be familiar with logarithms to simplify this further, or use a calculator. And eventually, this is the maximum information possible. It's 1 bit for this binary variable because it's a fair coin. So we have the maximum randomness because it's a coin that is fair, and I toss it and I cannot predict which one is more likely, heads or tails. So it's the maximum randomness. You can obviously also have loaded coins, manipulated coins, where you say, for example, this is 90% and this is 10%, or this one here is 100% and this is 0%. And you will see that the randomness goes down. And for this, I also have an example in the slides. So the fair coin is just something we've looked into. You could have a loaded coin that is always heads. So you flip it, it will always be heads. And it turns out, you can try this at home, just from the formula we've seen, the entropy would be 0 bits. So absolutely no randomness. The concept of entropy will be needed now when we study the importance function. The importance function will build a little bit on top of that. And what we need is now, we need a binary entropy for our data. I think I will also derive this with you on the iPad. So we have our data, and remember from the data before, we had a certain number of examples. Some have a true label, some have a false label. So the attack label. I also have the data set here because we will later need it. So what we need now is the label, which is attack. And we see we have 12 rows and 5 of them have a true label in attack and 7 have a false label. We will now do this for our data, that we need the binary entropy for our data. Where we have Q, so we have probability Q. For the previous example, this would have just been, for example, e.g., for example, 7 out of 12, or no, it was 5 out of 12, sorry, because we had 12 rows and 5 were positive and 12, or the other 7 of the 12 were negative. So we could say, for example, Q would be 5 divided by 12 for the data set from before. And we can now calculate the binary entropy for our data set, which is B of Q, and it's minus Q times the binary logarithm of Q. So Q is just the probability that we have seen before, plus, and the inverse of Q is 1 minus Q. So here it would be 7 divided by 12 times the binary logarithm of 1 minus Q. When we sum this together, then don't forget the minus before here, because this comes from the formula of the entropy. Now we can extend this a little bit. So we have our data set from before. We've seen it here. We've said we have 12 rows, 5 are positive, 7 are negative. So we can just write this a little bit more detailed, and we can say we have, say, P positive ones and N negative ones. So the entropy of our goal is the target, what we would have in the leaves, which is true or false, so attacking or not attacking, the goal. This would be the binary entropy. Remember, it's this one here. And this probability Q would be calculated. I've said before 5 divided by 12, but I'll just formalize this a bit more. We would say we have P many positive ones in the goal, which are 5 divided by the sum of the positive ones and the negative ones. And as before from the example, so this could be 5, and this, for example, 7, just as example. So 5 divided by the sum of 5 and 7, so 5 divided by 12. Now we need one more piece, or two more pieces. We are starting with the entropy. But in order to calculate our importance, I've said we want the importance, and the entropy is part of the importance. But we need to define now how we can fully calculate the importance. And if you look in the literature, there are different approaches for the importance function. What we will do is the so-called information gain. The information gain can be calculated as follows. It's the information gain of our goal and an attribute A. Remember, we have to try this for the different attributes. We need to determine how important each attribute for the data set is. So A is here the variable. And I calculate this by calculating my binary entropy, as we have just done up here. So P positive ones in the goal divided by the sum of the positive ones in the goal and the negative ones in the goal. And we subtract something, because the entropy here is not enough. I need to subtract something, and that's called the remainder of A. Now, what is the remainder? The remainder is another information theory specific concept, and I'll show you how we define the remainder and why it's called remainder. I'll first write down what the remainder is. So the remainder of A is defined as follows. We have a sum with a variable from k equals 1 up to d. What is d? D is the number of unique values in A. So D, we say we want all the values in our attribute A. But I want the distinct ones, so the number of entries in that set. So values of A is a set, say the values 0 and 1, for example, and I want the number of values in the set. So I'm using these two signs here from set theory. So I'm going through with my index k from 1 up to d, where d is the number of distinct values. Then I have different subsets. So E is the set of my examples I'm currently looking at, this one here. And I want to know how many examples are in E. So what's the number of examples? So I need to look at the number of elements in that set. And now I'm looking at a subset for which there is my distinct value that I'm currently looking at. And I'm calling this EK. We'll look at examples soon, and then you see this is actually quite easy to calculate because I have my K, and I'm looking at the subset of the examples where I have the distinct value in, where K is 1, then and so forth. And I have a division of the number of elements in EK divided by the number of elements in E. And I'm multiplying this with a binary entropy of pk, where pk is the number of positive examples in the subset EK divided by pk plus nk. Why is this called the remainder? Because I have my entropy here, and I need to, this works on the goal, on the label. And then I go along that branch, and I need to add an additional, this one here, many bits of information to answer the question of what would happen if I pick A. And that's why this is called the remainder. And I'm subtracting the remainder from the entropy. So the key formula is this one here. There's also a slide where all of this is well formatted, if you wish, and where all what I have just said is written down and well formatted. And I think the best thing we can do now is we will actually look into an example. But we will do a quick break for 5 minutes, and then we'll continue with the example. So after we've looked at all these formulas, we will actually start calculating, and we have our training data set here, and we want to learn a decision tree based from that data. So what we need to start with is we have the whole data set, and we will now need to determine which of the 3 attributes is the most important one, and one we put in the root. Is it enemy visible, enemy distance, or enemy armed? So we calculate the information gain, and you will see that these formulas from before, they're actually not that difficult. We need to look at the whole data set, which I just denote here with a D, and calculate the information gain for the whole data set and the enemy visible. I just write visible, not enemy visible. We said one component is the binary entropy, or the entropy of the whole data set, H of D, sometimes also just denoted as B of D, but B and H are here just the same. B is the binary entropy, H is the entropy in general, but here these are just synonyms in the slides. So this was the first part, and we see it, we have distinct values 0 and 1. And we need to build these subsets. So the first subset would be rows 1 to 6, and the second subset rows 7 to 12. And we see I have 6 in the first subset and 12 in total in my data set. And I want the entropy of the subset where visible is 0. So I denote this here by h of d0. And I subtract, again, 6 divided by 12 as a factor of the entropy of the subset of D1. Now, because what we had here is, what I'm putting in blue, this is just a remainder. You could also just write this as a minus of that sum of the remainder, but I've just removed the 0 parenthesis and I say I'm subtracting the first part of the remainder and then the second part of the remainder. So it's just the formula from before that we had written down in the other sheet down here, which was just this one here where I'm subtracting the remainder. And in the remainder, I'm going through the distinct values in my attribute, which are here just 0 and 1. And I have these subsets and the entropies of the subset. It's actually fairly simple. Now, the entropy of D, we have 5 positive ones and 7 negative ones. So we say it's h of 5 divided by 12 minus this here and this. And now I need to know how many examples in the first subset are positive and in the second subset. So the first subset, enemy visible is 0. I have 6 elements. How many of them are positive? Like to see if you have understood this. Take a look into the first 6 examples. How many have a positive label and how many have a negative label? Send a number to the chat. If you don't see it, red reaction. If you see it, green reaction. So red for negative, green for positive. If you see what I want you to determine from the data set. So the first subset where enemy visible is 0 are the first 6 rows. And each of them has an attack label, which is the last column. And only one of them is true and the 5 others are negative. So the first one is true and the 5 following ones are negative. So I have 1 out of the 6 is positive. That's the probability. Now, the next subset, which are the rows 7 to 12, how many of them are positive and how many are negative? Let me know. Because row 7 to 12 is the next subset where enemy visible is 1. And 4 are positive and 2 are negative. So 4 divided by 6. Now, I need to calculate these entropies. And that's why you need to bring a calculator to the written exam, because you've seen before how we can calculate the entropy, which was this formula here. But you need a logarithm and all of this. So that's why you just bring a calculator to the exam. And it turns out that the entropy of 5 divided by 12 is something around 0.98, 6 divided by 12. The entropy of 1/6 is 0.65 approximately, and the entropy of 4 divided by 6 is around 0.918. In the exam, you should use 2 or 3 decimals in order to get the proper results. And then we have these fractions here, and the information gain is 0.196 for the visible attribute. The enemy distance attribute is the next information gain we need to look at, because we need to determine which of the three is the most important one. So we need to calculate the information gain of distance. The first part is the same, the entropy of the whole data set. But now I have 3 distinct values in distance. The first distinct value is less than 10, then 10 to 20, and greater than 20. And for each of those distinct values, I have 4 rows, because I have 12 rows, and rows 1 and 2 and 7 and 8 are from less than 10, 10 to 20 are 3 and 4 and 9 and 10, and the remaining 4 are for greater than 20. So I'm subtracting now 3 pieces because I have 3 distinct values in that attribute, and one is h of d that is less than 10. The next one is d of 10 to 20, and the next one is d, is greater than 20. Now, h of d doesn't change because we have our 12 rows, and 5 of these 12 are positive as before, because we're just looking at a different attribute. So just copying this, and we will put in these values here very quickly. So if you look at the data set with me and we look at the rows where enemy distance is less than 10, which are rows 1, 2, 7, and 8. It's 4 rows. How many of them are positive? We have a positive label. You can count this and tell me 3. That's correct. So it's rows 1, 7, and 8. So 3 of those 4 ones. Now the ones where we have values 10 to 20. These are rows 3 and 4 and 9 and 10. How many of them have a positive label? 2 of the 4 ones. And now where we have the value greater than 20, rows 5 and 6 and 11 and 12, how many of them are positive? It's 4 rows in total and 0 are positive. That's correct. 0 of them. Now, if you use a calculator, you will see that this is again 0.98 minus 4 divided by 12 times the entropy of 3 over 4. It's 0.811 minus the entropy here. So this is something that you can easily remember. 2 divided by 4 is just a half, or 0.5. And the entropy of a half is just 1. We've seen this before with the fair coin, so times 1. And the entropy of 0, so 0 divided by 4 is 0. The entropy of 0 is 0. And the entropy of 1 is also 0, because there's no randomness. So this would be just minus 0. And if you use a calculator, you will see that this is 0.376. If you do the same procedure for the armed attribute, I'm not doing this now step by step, but we have the solution in the slides. If you do the information gain calculation for our data in the armed attribute, you will see that this is 0.021. So we have these three information gains. Which one is the largest one? The second one. So the information gain for the data and distance is the largest one. That means our decision tree is something we can draw now. We do first a check on distance. Because we have the largest information gain for that attribute. And now we're getting into this recursive procedure from the algorithm that we studied. Because we have now found the most important attribute. So we've done this argmax we've just studied before. We found enemy distance is the most important attribute. And there are three distinct values: less than 10, 10 to 20, and greater than 20. So we have three branches in our tree: less than 10, 10 to 20, and greater than 20. Imagine the first distinct value we're looking at is greater than 20. So this is just the first one we are starting with. What do you notice if you look at the rows in the data set? So we're doing now a subset, because this is something we've also studied in the algorithm. We create subsets. And now the first distinct value we are looking at is greater than 20. And these are rows 5 and 6, 5 and, well, this 5 and 6, and 11 and 12. What do you notice if you look at the labels of the subset 5, 6, 11, and 12? They are all false. So we're doing this recursive call on that subset, but in the beginning of the recursive call, we check if all of these examples have the same label. That's something I mentioned before. So in that regard, we are done. So we can say here, greater than 20, we are done, and we have a leaf, and it's false. What we still need to investigate are the other two cases: less than 10 and 10 to 20. When we look at the examples, say the next distinct value we're looking at is less than 10. So we need a subset now, and the subset where we have the values less than 10 are the rows 1, 2, and 7 and 8. And we see we have different labels. So we need to investigate further. In fact, what we need to do now is we have the subset of the examples 1, 2, 7, and 8, which are less than 10. And we need to again look at the remaining attributes, which is visible and armed, and figure out which one to pick. Because we are building a tree recursively. So I'll show you how to do this. We need to calculate the information gain where we have the subset of the examples that are less than 10, and we have two attributes left: visible and armed. So let's start with visible. We will calculate this as the entropy of that subset. And in visible, we have distinct values 0 and 1. So we need to subtract the remainder. What you see is from the subset, which are examples 1, 2, and 7 and 8, 1 and 2 have the distinct value 0 in enemy visible, and the other ones have value 1, which are 7 and 8. So we have two elements out of these four ones where we need the entropy of that subset and visible is 0. And the other two of the four examples, we have less than 10, and we have the visible 1. So these zeros and ones, they come from visible. So we have example in the subset, elements 1, 2, 7, and 8. It's four elements. How many of them are positive? Or with a positive label. So we have four of them. How many are positive? Tell me in the chat. So rows 1, 2, 7, and 8. Three are positive. So three of the four ones. Now we look at this subset, the ones that are less than 10 and visible is 0, and the ones, so we start with this one, which are rows 1 and 2. It's two elements. How many are positive in rows 1 and 2? 1. And the other subset is 7 and 8, both are positive. So here, 1 out of 2 and 2 out of 2. So if you use a calculator, you will see that the entropy of 3 over 4 is 0.811 minus 2 divided by 4. The entropy of a half is again 1. We've seen this. And the entropy of 1 is the same as the entropy of 0, which is 0. So we have 0.811 minus 2 divided by 4 times 1, so minus 0.5, so this is 0.311. The other attribute we could investigate is armed. And if you do these calculations, you will notice, if you do this for armed and you see the details in the slides, it's also 0.311. So what would you do if, and these are the only two attributes left. What would you do if you have two attributes and both have the same value, so there's no maximum one? What would you do? Send some suggestions here in the chat. Because there is no largest one. I somehow need to pick one of these two. Do you have a suggestion if what you would do? If you have a suggestion, maybe turn on your mic or send something to the chat. If you have no suggestion what to do, maybe send a red sticker. So here I'm just unable to advance. So I need to pick one randomly. There's nothing else I can do because I only have two left and they have the same information gain. So I pick one randomly. If you do this in the exam, you would just also write, I'm unable to distinguish, so I just pick one of them randomly. Now I say I pick visible randomly. Say I pick visible. And visible is 0 or 1. So I need to do something for 0 and something for 1. Now we look at our examples. Remember, it's the subset of those where enemy distance is less than 10. And I've picked visible. When visible is 1, these are examples 7 and 8, which are both true. So when visible is 1, I'm done. I have my leaf, which is true. But when visible is 0, these are rows 1 and 2, and they have different labels. So I still need to pick enemy armed. And enemy armed is the last attribute I can pick. So what I need to do is I need to put here armed. And now I have little space down here. So I need to highlight this in some way. So down here, I still need to do something. We see the solution in the slides later. And what I can also put in blue are actually the leaves where I make the decisions. So here I'm not fully done yet. I still need to do something in the recursive call. And I also need to do something here where distance is 10 to 20. So we're almost done. There's just a little bit of more work to do. And I'll show you this in the slides. So what I had shown you is we picked distance as the root. Then we checked where we have in the distance less than 10 for the visible attribute, we got 0.311. If you do the same calculations for armed, it's 0.311. So we picked one randomly. And we did this one here. We've also done where there is greater than 20, it's false. And where it's 10 to 20, you still need to check whether to put the visible or the armed attribute. And it turns out for visible, the information gain is 1. It's just the same calculations, just the same procedure we have done before, just for the subset of 10 to 20 and then the visible attribute. If you pick the armed attribute, the information gain is 0. So here it's quite easy. You pick the visible one. And if you do these few more calculations that we had just skipped here in the slides, eventually you will get this tree. So this would be your homework because all the solutions are here in the slides. We just skipped a few of the slides. Try to do the decision tree learning on your own again. You see all the solutions in the slides. We've done 2/3 of the calculations now on the iPad. And do the remaining calculations. All the solutions are in the slides, and you should come eventually to a result that is this decision tree. And what you should revise in detail again is this algorithm, because we've now applied it. I know it's tricky, but what is important is we are finding the most important attribute, so the importance function. We use the argmax. We've picked an attribute. We go through the unique values in the attribute, learn subtrees, and we pass our subsets. So this was this D less than 10, D 10 to 20. We pass all the attributes except the one we have just picked and keep doing this recursively. So this is also a good revision for recursion. And eventually all the numbers are here that you need to calculate this, and you will come to a decision tree that looks something like this. If you have more time, there is another data set. It's a data set about whether you should wait at a restaurant. It's something like there are lots of variables. So you want to go to a restaurant, the restaurant is full, and you would determine whether it's worth waiting until there's a free seat or not. So there are alternatives nearby, whether the restaurant has a bar that is comfortable to wait, whether it's on a Friday or Saturday, whether you're hungry, and some other variables, and an estimate of how long you need to wait, and you will decide whether you should wait or not, which is true or false. So this is the label, the last column. And here you have 12 rows, and you need to learn a decision tree. Calculating this by hand will take a little bit of time because you need to calculate all of these information gains, and some of these attributes are binary, some are not. So calculating this by hand will probably take you quite a while. This example would be also way too big for the exam. So in the exam, if you need to do decision tree learning, this would be about smaller data sets. But this here can be a good practice for you, but this is not a mathematics course, it's a computer science course. So your task is also to turn all of this into code. So when I have implemented decision tree learning on my own, I have implemented this algorithm, I think twice in my life. I have applied it to this data set, and eventually I got a decision tree of something like this. Based on the attributes, I will decide whether I wait or not. So the leaves are the decisions. I wait or I don't wait for the restaurant to have a free seat. This is the tree that I got when I implemented decision tree learning. And this also brings us to the coursework. The coursework has an exam bonus problem. What you are tasked with is a completion of problem 12.6. So 12.6 within this sheet, where you have the decision tree learning algorithm. And it's your task to implement this for binary attributes. If you wish, you can also do this for attributes that are multi-valued, but the label is always binary, and come up with a data set of your choice. What I want you is that you implement this decision tree learning algorithm on your own. So you're not allowed to use a machine learning library like scikit-learn to implement this. You can use other libraries for pre-processing your data or for visualizing your tree, but the actual tree learning is something you need to implement on your own. Eventually, you just need to turn this pseudocode algorithm into concrete code, implement the importance function, which is your the information gain, and it's a little bit of code to get this to work, but it isn't that difficult. If you do this and you can implement this in, or you implement this in a Jupyter notebook, you pick a data set of your choice and you visualize the learned tree, this would be your bonus problem. You can do this in a group of up to 4 students, and you would submit an HTML export of your Jupyter notebook, and you can submit this until July the 1st. If you do this, this carries a 10% bonus for the exam, so can massively help you to improve your mark in the exam. If you don't do the bonus problem, no problem. You can still reach the maximum mark in the exam because it's a bonus for the exam. Because one student sent me an email yesterday asking about the exam bonus problem and the mandatory problem. You're now able to do the exam bonus problem. The mandatory problem is something you were able to start a long time ago because these text pattern matching algorithms are something you would study on your own in the book and then implement it. And all you need to know for this is maybe complexity theory and Python. So you could have started the mandatory problem long ago, and you also do this in a group of up to 4 students. You can do it alone if you wish, or together with 3 others at the very most, and you would also submit an HTML export of your Jupyter notebook. Very importantly, never submit a Jupyter notebook because I won't be running your Jupyter notebook for security reasons, but you can export a Jupyter notebook as an HTML or also as a PDF if you wish. And then I will look at that export of what you have run. So submit an export of the run Jupyter notebook. Do not submit a Jupyter notebook because of IT security. Who of you has already started with the mandatory problem or has already started or completed? Send me maybe a green sticker if this is something you have already looked at. So quite a few. And now you're also able to do the exam bonus problem. And for the student who has asked me like what you're already able to do, I refer that student to today's lecture. So this person is either here live now or will watch the recording later. The coursework comes with a few more things. So I talked about the coursework about trees last week already and said problem 12.1 is something you could do after last week's lecture, including the 12.2, the inversion or flattening the tree. And now you're able to do 12.4 and 12.5. So 12.5 is something you would do manually by hand on this data set and try to learn a decision tree for the attack label. Data sets of that size is something you may be tasked with in the exam to learn a decision tree. And if you have some practice, this will take you 10 or 15 minutes at the most to learn the decision tree manually. And 12.6 is then the high-end problem in which you implement that algorithm and you run it, and then you can automatically learn your decision tree. And this would be the bonus for the exam. By the way, the exam, I had never talked much about the exam in this lecture, and today I want to say a few words because the exam is getting closer and closer. As you know, the exam is on July the 14th, and what you find in my Nextcloud directory are the past exams of since I started teaching this course 5 years ago. My exams look the following. My exams have 3 problems, and then you pick 2 out of these 3 big problems. Each problem carries 25 points. You pick 2 problems, so you can score 50 points at the most, which is a 1.0. If you score 49 points, it's a 1.1. If you score 48 points, it's a 1.2, and so forth. So I have a table for this. I'll quickly show you this. And this sheet here about how I mark exams is also available in my Nextcloud directory. Say you pick problems 1 and 3, you score 44 points. 44 points is a 1.6. But 1.6 is not a valid mark because in our university, we only have valid marks 1.0, 1.3, 1.7. So I round this to your advantage. If you score 44 points, it's a 1.6, which is rounded to a 1.3. If you do the exam bonus, you can score 10% on top. So since you can score 50 points at the most, if you do the exam bonus, you get 5 points on top. That means if you have 44 points, I add 5 points on top, which is 49. It's a 1.1, which is rounded to a 1.0, the best mark possible. So the exam bonus can help you to improve your mark quite a lot. One thing, I told you should pick 2 problems. If you do all 3 problems, if you have time left, so you pick 2 problems and then you work on the 3rd problem. If you work on all 3 problems, the best 2 problems count. So for example, this student here, this example, one student got 24 points, 5 and 20. Then the best 2 count, which is 20 and 24, it's 44. And you can look into the past exams in Nextcloud. Has any of you already looked into past exams? If so, maybe send me some reaction, green or red. There are various rules here that you need to read, and you're only allowed to bring 2 helpers. One is a non-computer algebra system calculator, so a regular calculator that can do logarithms and fractions, but not a computer algebra system. And you can bring a one-sided handwritten A4 note sheet with any notes that you wish, but must be one-sided, must be handwritten in A4. And for example, you could write down the formula for the information gain if you wish. If you think you don't remember this one, maybe write that on your note sheet. The rules are there in English and German. You can, and all the questions are asked in English and German. You can answer in English or German as you wish. Ideally English, because that's the course language. But if you wish to answer the questions in German, that's fine. And then each problem is 25 points. So, and there are sub-problems in here. And you would write in this box, and you pick 2 out of the 3 problems. Towards the end of the term, we will be studying last year's exam together. So I will announce this date in early July. We'll be studying last year's exam together and discuss your solutions and my solutions. If you go to the tutorial taught by my teaching assistant, she also discusses past exam problems with you every week. So that's something to get extra practice and familiarize yourself in the coming weeks with the past exams, because we are progressing now with the content and we have done like 2/3 or 3/4 of the course content. So you'll be able to work on most of the exam problems now and do all the coursework. So we have finished now trees, and we've seen trees as a data structure, for example, to have search trees, and we saw that we can search in search trees very efficiently if they are balanced. We looked at how we can traverse in trees, and as one concrete application of trees, we've looked into decision trees, which is a machine learning algorithm. We can learn a tree or a pattern from a data set, and we can use such a decision tree to make decisions. Like a tree like this, we can always use it to make decisions when we have a new instance, and we'll come to a decision. And these decision trees that we learn are relatively compact. They are not optimal, but approximate, and they allow us to make decisions very easily. And we can also visualize the tree so the decisions are explainable, and overall decision tree learning runs very quickly, as well as predictions are quick. So you got to see now one example of machine learning, and that trees are actually helpful, not just for the foundations of algorithms and data structures, but also to solve problems in AI, since most of you are studying AI. And those of you who study cybersecurity, you will also need plenty of AI in your career. Now we have one more essential data structure that we start discussing today. We want to explore hash tables. Hash tables are something we've been using in Python all the time, which are these dictionaries. And these are, again, a very helpful data structure. We will start building it, and later we will compare it to trees. So trees are a very efficient data structure for searching data, like balanced search trees. We saw that if we're able to sort our data and we're able to balance the tree, we're able to look for data or look for data in a logarithm amount of time. So that's something very helpful. Maps and hash tables are a totally different approach, and which are also super helpful for very efficiently storing and retrieving data. We will start building this today. We'll continue next week. And then once we have built the hash tables, we will compare them to trees and discuss pros and cons of both approaches. What we want to build initially are key value stores. So that's something you've seen in the Python dictionaries, that I have an entry that has a key and a corresponding value. And I can query for the key and I get the corresponding value. We will start building this, and then we try to improve it by using hashing and building hash tables. But it could happen that when we start hashing the entries, there could be collisions, and we will see how we will handle this. And then you will have a good understanding of how hash tables work, which are the Python dictionaries you've been using all the time, and they are integrated in Python, but now you'll see how to build your own ones. We are starting with a simpler concept, which is just a map. So hashing will come later. We are starting now with key value stores. And a map associates keys with values. And there's one constraint that keys need to be unique. So values don't need to be unique, but keys need to be unique because later we want to query or override for a key, so keys need to be unique. And a map could look something like this. So we have keys, which are country names, and we have the corresponding currencies, which are the values. And we see Turkey is the key and lira is the value. China is a key, yuan is the value. And we see Spain is the key and the corresponding value is euro. And Greece is another key and euro is the value. And the keys need to be unique. The values are not necessarily unique. Because it makes sense that we require the keys to be unique because imagine a key like Greece referred to multiple entries, then we wouldn't know which one to pick. So unique keys, and we associate them with values. And this is exactly implemented in your Python dictionary class. And we'll see now today and possibly next week again how to build this. So let's start with maps. And for this, we need an abstract data type again. And we will study now the most important behavior, and then we see how we can turn this into code. So a map M, we can return a value. So we use map and index k. K is the key, and we want to return the corresponding value for that key if it exists. If it does not exist, we will raise a key error. And in Python, this is implemented with the getItem method. You've seen getItem already when we implemented lists. Do you still remember getKey from the lists from a few weeks ago? Maybe thumbs up or thumbs down. Or green or red, whatever. It's also in the coursework. So when we looked at lists, we looked at the getItem as an index. And this is now something we also want for a map. We also want to be able to associate a value with a key. So we want to be able to add a new key value pair, like in the Python dictionary. We say the map of k is a value v, and this adds a new key value pair or overrides one that is already in. So one for which we already have a key, we would replace that key value pair with a new key value pair. And this would be done with setItem. And I also want to be able to remove a value from the map. And in Python, there is a keyword that is called del, and you can apply del, for example, to m on index k, which would remove the key value pair for key k. If there is no such item, we would also raise a key error. And in Python, this would be the delItem special method. We did not implement delItem for the lists. For lists, we did getItem and setItem and this kind of stuff. But feel free to implement for the Python lists also the delete item method to get some more practice. We will have two more helpers that we need. We also want to get the length of the map, so how many key value pairs are in there. And we also want to be able to have an iterator on M, and this would generate a sequence of the keys in the map. Not the values, but the keys of the map. So for this, we need to implement the iter method, which is also a special method in Python. What we are now using is also inheritance. Inheritance is something do you all feel okay with inheritance from your programming course? Maybe thumbs up or thumbs down. It's anyway something we revised very briefly when we started this course 2 months ago and had an intro to Python. But I see from your responses you're all fine with inheritance. What we want to do is now we implement a couple of classes. We will start with a map base, which is the first class we're probably, or one of the first classes we're implementing, which is a base of different mappings. And step by step, we will build more complex maps until we get to hash tables or hash maps. So we need a map base, which is very basic functionality in maps. And then we will have more concrete maps, like an unsorted table map, which is something you will see soon. And then we want to introduce hashing. We will have a hash map base, but there are different ways how we can handle collisions in hashing. And there are two approaches, and we will implement one of them. And we want this to be part of the Python ecosystem. In Python, there is a collections module. And in the collections module, there is a mutable mapping. And it's a base class, an abstract one, in fact, that we cannot instantiate, but we want to inherit from it and have our map base, which will add some more functionality that all of our maps that we implement next are actually then using. Like the unsorted table map, the hash map base is abstract. This one here will also still be abstract. So the concrete ones that we can use later is the unsorted table map and the chain hash map. The book, so this figure here is from the book. The book also introduces a sorted table map and a tree map, but this is something we're not implementing. And we are only implementing the chain hash map, not the linear probing. It's just a different strategy how we can handle collisions. So we can start to code this now. I will share my Jupyter, my IPython session very quickly. We got a question here about the cheat sheet for the exams or the note sheet. Last year, some students asked if they could write this on an iPad and print it out. That's also fine if you use handwriting, but you should not, or you would not be allowed to type your note sheet and then print it. But if you handwrite it on the iPad and print it, I'm okay with that too, or iPad or some other tablet device, obviously, not just iPad. Hope this answered the question here. So what we need is now our map base. And we saw in the inheritance tree that the map base inherits from mutable mapping. And there is the mutable mapping class in the Python's collection module. Actually, the collections module has a submodule which is called ABC. Anyone has a clue what ABC stands for in the context of object-oriented programming? So ABC. If you think you have a clue what ABC could be, maybe thumbs up or green sticker, then I'll wait for you to answer. If you don't know what ABC could be, send some negative reaction. So why is this called collections.abc? And I'm waiting for your reactions, either positive or negative. So we got a green reaction. Then tell us what ABC stands for. You can turn on your mic or write it as you wish. That's correct. It's an abstract base class. So a base class that I'm unable to instantiate, but it offers some general functionality. And when I inherit from an abstract base class, I still need to implement certain pieces. And then if that's done, I'm able to create objects from the class. And immutable mapping comes from abstract base classes for collections. And we will now try to implement our map base, which inherits from mutable mapping. And what we have is in the class mapBase, we have an inner class that we call underscore item. So underscore again denotes that this should be considered private. It's not private, but we want it to be considered private. So we say class underscore item is an inner class of the mutable mapping. And we will now we are creating now the instantiator. So we want a key value pair to be, or the items are key value pairs. So a key and a value. And we are storing this. So we say key is, the key is stored in underscore key attribute. And so here my IPython still remembers the implementations from last year. And I'm storing the value in the underscore value attribute. There are a few more features we want to implement for our key value pairs. We also want to be able to compare two entries. Maybe you noticed from Java, there is the equals method, which allows you to compare two entries. Has anyone seen this in Java, the equals method? So we're able to compare two entries, so I get some positive reaction. So, and the equivalent here in Python is the EQ, but it's a special method, so starts with two underscores and ends with two underscores. And I want to be able to compare my item to a different item, to the other one. So what I'm returning is, I'm saying, I want to check if my key is the same as the other entries, as the other item's key. And this returns either true or false. We will later need this functionality when we add new entries. And as we can check for equality, we can also check for the opposite. We want to check if two entries or two items are not equal. So what I'm returning is just the opposite of the equality. So I'm checking if my current item object, so which is self, is the same as the other one. So this expression here calls the equality method, and I'm inverting the result. So self equals other uses the equals method. There's a question if in compared to Java, in Java you would implement the hashcode method. If we also need to implement this, if we implemented equals. I know in Java there's the hashcode method. Here in Python it doesn't work this way. We will later implement the hashcode differently. All we need to do right now in Python are the equals and not equals, as well as the less than. So less than helps us to bring order in our items. And I want to check if one item is less than the other item. This will later help us to bring order between items. This is also something that you could do in some other programming languages. And here it's natively supported by Python. And I'm checking if my key value is less than the key value of the other element or the other object. So this is highly generalized functionality that we are unable to use directly now. It's just the hash map base that includes now our items, because we've specified that we are storing key value items like this in a mutable mapping. So we've created our map base class inherits from mutable mapping. And in there, we've specified what our items could look like. And later we will be able to compare items. They are equal if their keys are equal. They are not equal if their keys are not equal. And remember, self equal other just calls the equal method here. And we're able to bring in an order by determining if one item object is less than another one, and we do this comparison based on the key. Now we will implement an unsorted table map. And what is an unsorted table map? It's eventually a list in which we are able to store key value pairs. So a list in which we're able to store objects from our item class. We can implement this, and before we looked at that inheritance tree, and I think we'll just look at it briefly again, just to make sure we are all on the same page. We are implementing this tree. We have just implemented the map base, which inherits from mutable mapping. And in here, we have our item class, which helps us to store and compare and bring order between key value pairs. Next, we are implementing an unsorted table map, which is eventually a list in which we are storing objects of the item class, which is in here. So, and later we're coming to the hash tables, but we are building this step by step. So my unsorted table map inherits from map base as shown in the figure before. And I am initializing my unsorted table map object. And what I have in there is a table. It's eventually just a list, initially an empty list, and it's just a regular Python list, and we keep adding elements to it, following certain rules. I'll explain this now. We are starting with our length, and the length is just the length of the table. Because before we've defined this abstract data type, and all we are doing now is we're implementing the length, the iterator, as well as adding and getting and deleting items. So you remember the abstract data type just from a few minutes ago. What I need is I want to get an item. So I want to get the value for the corresponding key K. Since in this initial unsorted table map, I have a list, what I need to go through is I need to go through all the items in my table, and I need to check if that key is equal to the key of the item. If I have found an item for which the key matches to the key I'm looking for, I am returning that item's value. What should I do if I'm unable to find that item for which I know a key? So if there is no item for which a key matches, what should I do? Should I just stop or do something else? If you have a suggestion what we could do, we've discussed it before when we looked at the abstract data type, tell us. I'll see if one student suggests we return none. We could return none, but then we would check if none was returned and somehow handle this. But a better mechanism is we raise an exception. And this is also something we had done, for example, when we implemented lists and an index was not valid, we didn't return none, but we raise an exception. This is, I think, the much better approach, because then the exception needs to be handled properly. Because if we just return a none, maybe this just gets ignored and the code keeps running, and actually we're in an invalid state. So better raise an exception. As we are able to read items, we also need to be able to, so we're able to read items now. We also need to be able to set new items. So we can add items and we can say my table, I'm appending a new item. So I say my table is my list. I'm appending a new object of class item. I can say self dot underscore item because my unsorted table map inherits from map base, and map base has this inner class underscore item, which is therefore also an inner class of unsorted table map because we inherit from map base. So I'm creating a new object of class item and I pass my key value pair here to the constructor. But set item can do two things. When we looked at the abstract data type before, we can add a new key value pair or we override an existing one. So what I need to do first, I need to check, is there already that key in my list or not before adding something. So I need to go through all the items in my table and I need to check if I find an item for which the key matches to the key I've put here. And if that's the case, I'm not allowed to add a new key value pair. Rather, I need to override the existing one because we said keys need to be unique. So what I can say is I'm just using the the item object from before that I have found, and I'm taking that item and I'm overriding its value with the new value. And if this case has happened, I'm unable or not allowed to continue because if I continue from here, or if I continue here, I would still add the new key value pair. So I'm just returning. And returning here means I'm just finishing the method and I have overwritten the value. If the loop runs through and this condition never holds true, then I will be appending the new item object. So we're able to set an item. We also want to be able to delete an item. And what we need to do is we need to check if there is an item with our key K already. And if so, we would be removing the whole item object from the list. So there are lots of ways how I can implement this. Here I will use an index j, which runs from 0 up to n-1, where n-1 is included, or up to n, where n is not included. So I'm using a range on the length of the table. And I'm checking if my key matches the key of object K, of object J. So J is my index. And I'm checking for each entry in table the key if this matches my key K, and if so, I am popping entry J and I'm done. So popping means remove J. As you may remember from our complexity theory chapter, when we studied lists, when we studied lists and knew about complexity, we saw pop element J is not that efficient because we may need to move some elements around. But the way we will be later using the unsorted table map will be, we will use a lot of very short unsorted table maps in a hash table, which will be the next data structure to be implemented. And once we do this, all these unsorted table maps will be relatively short, so the impact of this will be relatively small, but we'll study this later. We will assume later that these unsorted table maps we will have many of them, and they will all be relatively short. So now assuming I have not found an key K for which I'm supposed to delete the item, what should I be doing here again? So I have passed a key, but I could not find the corresponding key value pair. Before, someone suggested what we should be doing when reading. What should we be doing when deleting? Let me know what you think, how you would handle this problem. Any suggestions? What I should be doing here if I'm unable to find the item that I want to delete? Maybe send me some reaction if you see what could be going wrong, or send any comments what we should be doing. And again, one student suggests erase an error or do nothing. Well, don't do nothing because we are relying on correct states. So yes, we should be raising a key error again because we're trying to delete something that does not exist, would be an invalid state. And the last thing the abstract data type wanted us to do was we build an iterator, or we're able to have an iterator on the keys. So I would go through the elements of the table, and we're now implementing the generator. So we would generate each element just in the order they are stored in this table. And I'm using the yield statement on the keys. And I have actually now implemented my unsorted table map. We can test this. We can say we are instantiating the unsorted table map. Initially, it's 0 entries. Say we're storing, for example, something like this. We have the key. It's an integer and the value is a string. We do this for a couple of other entries. So 1 data 10 is 10, something like this. We have now 3 entries in it. We can read them out and we can try to delete them. Now we have 2 entries left. We can try to overwrite. So data of 10 is now the updated value. And we could also be using the iterator if we wish. So I is the iter of my data. And then we get the next key, and then the 1 and 10 because the 5 was deleted. And here we get the stop iteration exception. So behavior looks okay. And obviously, we could also try to read out something that doesn't exist. We get a key error. Same for deleting something that does not exist. So implementation looks okay. And you also find the implementation as usual in our resources file in Nextcloud if you wish. So now we have a very, very simple map. Does not work, or it works very simple and offers us to build a key value store. But the dictionary class in Python works better. And we will now look at a couple of challenges we are still facing. And for this, we're looking in the slides. So the unsorted table map, something we have just implemented. And the unsorted table map, yes, gives us a very initial key value store, but it's not very efficient yet. What I want to build is, say, a lookup table. And imagine I have a lookup table that has 11 entries. So entries 0 to 10. And such a lookup table here has length 11 and it contains various items. It contains items 1D, so the index is the key and the value is a D, 3 set, 6C, and 7Q. It's a very simple lookup table where we say the index is the key and the value is stored in this list. Now, with such a lookup table, it's not the unsorted table map we've implemented. The unsorted table map we've just implemented is okay, but we'll introduce a new concept now, and then we see how we can combine this together. Imagine I have a lookup table like this. I can do lookups very efficiently because the integer is just a key. It's something I was not able to do with my unsorted table map because what I added to the unsorted table map were objects of class item. Here, my key is always an integer and my value is something else that I'm storing in there. Now, with such a lookup table, I can do very efficient lookups because it's just a list and I have an integer index and I can look up this in O of 1 because all I need is the index and I get the corresponding value. Now, such lookup tables are very fast, but imagine I have, like here, I have 4 entries in it in a lookup table of length 11. And imagine I need some big integers now, like integer 10,000. I will need to create a much bigger list just to have that one lookup index or this one index I needed as a key. So I'm creating a very, very large list with lots of empty spaces in between. And anyway, I always require that my index is my key. So I'm only allowed to have integer keys in here. And I may waste a lot of space. So I can do very efficient lookups with this, contrary to the unsorted table map, because in the unsorted table map, I have to walk through the whole list in order to find the element. I was able to have keys and values that are not necessarily integers. Here, my keys have to be integers, and I may be wasting a lot of space if I need a very big key, because I need to reserve a very big index, and this is just an array list. So not too great yet. And this will bring us to the concept of hashing. And the hash table will be the next data structure we're building. It's building on top of the unsorted table map. And what it has is a hash function. And the hash function maps keys to a corresponding index in a table. So it could map an integer to an index, but it also could map a string or some other object to an index in the table. So I could have, for example, a key, which is some string, and it would be converted to, say, index 7. And that string would be the key and value would be Q. So this is something that a hash function can do for me. And I have visualized this here. The hashing also allows me that I don't need to reserve a super big list up front, but rather I'm somehow converting the keys to indexes. Say, for example, index or key 1 is index 1. And what I have now at each index is a so-called bucket. And in a bucket, I may be storing multiple key value pairs. So key 1 is mapped to the bucket in 1, and its corresponding value is D. We see the same behavior with 3. 3, F is in bucket at index 3. 6 and 7 are also at the corresponding buckets. But I'm able also to map larger integers to some index like 25 and 14 are also in this bucket, or 39. You can maybe guess that all I need to do here with this very simple hash function is a modulo operator, because I have 11 indexes, so I can say 14 modulo 11. This will give me index 3. 25 modulo 11, because 11 is the length of this hash table, is so 25 modulo 11 is 3. Because 25 minus 11 is 14. 14 is still too large, so I subtract 11 again, which is 3. And 39 modulo 11 is 6. So a very simple hash function would just be a modulo operator, because I take the integer modulo the length of the hash table. This very simple hash function is not enough for reality. There are lots of different hash functions proposed in the literature. For example, this hash function, just using a modulo operator, only works if I have integer keys. If I have a string key, this doesn't work, because I cannot just take a string and take it modulo 11. But I could take a string and somehow convert it into an integer. This would be a very simple hash function. It doesn't matter what it does exactly, but it uses some bit shifts and goes through the characters in the string and somehow manipulates bits in order to convert a string into some hash value. And that hash value would be some integer that I've calculated from the string. And that hash value would still be taken modulo 11, and then it would fall into one of these buckets. And when I have multiple entries falling into the same bucket, this is what I actually call a collision. So collision means multiple entries or multiple keys have the same index in the hash table. Later, I need to see how I can handle collisions, because yes, a hash table simply, in the most generic concept, has a bucket. I have multiple entries at the same index. But how do I store them exactly? This is a different topic, something we will later see when we look at collision strategies. And it turns out that in Python, there is already a quite helpful hash function available. So hash is a native function that comes with Python. You can pass, for example, a string to it. You can pass some integer to it. We see an integer is just returned, so the integer is not turned into a new value. But if I pass a float value, I get some hash value. And I could try to pass other objects. And this is where this hash code method that someone mentioned in the chat before from Java would come into play, that I'm able to have a class and I have some object in stored, or some value stored in that object, and the hash code method would allow me to turn that object into some hash code. Something we're implementing here in this course slightly differently, but we see I'm able, with the native hash function in Python, I'm able to convert a string or a float into a hash value. And I could just take this modulo 11 to get a corresponding index, and also my string hello. And hello world would give me a different index, because a different hash code, and then modulo 11 would give me a different index of where to store it. Now, this concept of buckets is something I want to implement with you, because we still have 19 minutes, so there should be still some time to start implementing this concept that we have a hash table with buckets. Yes, there are collisions that multiple entries are in a bucket, and we need to think about how to handle such collisions, but this will come next. Because if we go back to our inheritance hierarchy, we said we want a hash map base. It's again a generic class, and this will have generic features of different hash table types. There are collisions, so there will be these buckets where we are storing the elements, and how to handle the collisions exactly, for this we will have concrete implementations. But these concrete implementations all have a lot in common, so we will implement now our hash map base and see what this generic functionality could look like. So we will implement our hash map base, which inherits from map base as shown before, and our constructor looks something like this. What it means is the hash table will have a capacity, or will have this width of a certain number of elements, number of indexes. We can say 11, whatever. And in order for our hashing to generate as little collisions as possible, we need to do some tricks. And something that is often used is that we add a couple of features to the hashing. And part of this is a prime number that would be added into the hashing in some way, as you will see soon, because we want to reduce collisions. We want to spread out these items, these key value pairs, very well in the hash table. And we don't want to run in a situation where we have a lot of buckets that are empty and a few buckets which contain a lot of elements. Rather, we want to spread it out. I need my table, and my table will be created up front. The table is eventually just a list, as we have seen the visualization. And initially, there will all be none entries in that list. And we have capacity many, which are 11. And that's our capacity. Initially, we have 0 elements stored in the hash map base. We have this prime number. This anyway is a default parameter. You can change it. This one here is just one example prime number that comes from the book, just a big prime number. You could also pick a different prime number. And we need 2 more concepts, which is a scale. And the scale and the shift doesn't matter too much in this course. What scaling and shifting does, we are just working with this prime number, and we're using a range. We're getting a random value from a range, and this will be a scale and a shift, and these will be values added in our own hash function on top, or it will be added and mixed up with the hash code that is calculated by the Python hash function. And all this will help us to do is that we want to have less collisions and spread out our elements as much as possible. The rationale of our own hash function is not that important now. It's just something that the book recommends. So we have a key K, and yes, we could just take, if in the most simple one, if we wanted, we could just take the hash of our key, and we could say we take this modulo, the modulo the length of the table, and this could be perfectly fine. But because hash will give us some big hash code for our key, and we want to find a proper index for it, so we take this modulo the length of our table. But I've just said we want to spread out a little bit more. And what the book recommends is, but this is again, it's explained in the book in greater detail, but it doesn't matter for this course. We multiply this with a scale, we add a shift on top, and then we are taking this modulo. So we could take it modulo the length, but the book first takes it modulo this large prime number, and then modulo the length. But this doesn't matter for the remainder of the course. It's only a strategy of how we can spread out the key value pairs more and have as little collisions as possible. We also want to know the length of, the length of our hash table, which is fairly easy. It's just n many elements. Oops, I'm sorry. Clicked enter too often. And there are a couple of more features that we can generalize. What I want is, I want to get the item for key k in my hash map base. So a generic functionality for hash tables. What I need to know is, I have my key k. What is the hash code for k? So I'm calling my own hash function on k, the key, and this gives me an index j. And now I need a new helper method, which I call bucket get item. It's not implemented yet. And in this generic hash map base, we're not implementing it because it's a feature we will later implement in our concrete hash table implementations, because I told you there are different strategies how we can handle these buckets. So all I want to know is there is a bucket at index j, and what I want is I want to get the element for my key k. And there may be collisions. That's why at that index j, there may be multiple entries in the bucket. And that's why I need to pass two parameters, bucket j and my key k. How these collisions are resolved exactly doesn't matter for now. Something that we will see next week when we implement concrete collision handling strategies. I also want to be able to add a new entry. And to add a new entry, I need to know the index. So I call the hash function again on my key. And then I need a new helper method, which is bucket set item. And there is a bucket at index j in the table. And there's a key value pair that I'm adding. So that's why bucket set item. What can happen now is, I want to visualize this for you. We've seen this visualization here of buckets. If you keep adding more and more elements to the hash table, eventually it will lead to a situation where these buckets all get quite full. And many buckets may have dozens or hundreds of elements. And no matter what collision strategy or collision handling strategy you have, this data structure will become inefficient. We look next week at complexity, but what I need to do is, if I keep adding elements, I need to grow this. Growing means not just 11 indexes, but more. So I need to resize in order to make sure that this data structure remains efficient, which we see next week when we look at concrete strategies. So I need to check if self.n is larger than some threshold. The threshold I'm defining for now is, say, if the number of elements is greater than the number of indexes divided by 2. We could also put some other threshold there, but next week we discuss why that threshold is actually recommended. So if we have more elements than half the size of the table. So imagine we have 11 elements and I have more than, or we have a capacity for 11 elements, and I have added more elements than half the capacity. This is something that the literature recommends, and next week we will discuss why this makes sense. And if we have reached that threshold and we've added elements more and more, and we are now up over half the capacity, then I'm doing a resizing. And resizing is something, for example, the book says 2 times the length. Why do I subtract 1? I could just leave this aside, but subtracting 1 helps that we have an odd number, because if I double an integer, it will be an even number. And if I subtract 1, it will be odd. And odd will help with this one here, with these modulus and with the prime numbers. That's why we started with 11. You could start with 10, but an odd number is actually better to spread out the elements more. And that's why I'm subtracting 1 here. You could also just add 1 if you wish, or subtract 1. It's your choice, but an odd number is better. We need to do 2 more things. We also need to be able to delete an item. So we want to delete an item for which we have the key K. I need to find out again which one is my bucket, and that's at index J. And I want to delete at bucket J the K key. And after I've deleted it, I subtract 1 from n because we have deleted an item. Obviously, reading out an element or deleting an element that does not exist, this has to raise exceptions. But this is something we investigate when we look at concrete strategies of how to manage these buckets and how to handle the collisions. And there we will also add the exceptions then. The last one is the resizing. Resizing is something we needed here because we had added elements and we have reached a threshold. So what I need to do is I need to move, or I create a new table. So I'm creating a new table with C elements, where C is the new capacity. And I somehow need to keep the old values before. One choice could be, I'm calling self.items. Self.items returns me all the items stored in my data structure. It's something we have not implemented yet, but it's a feature we're benefiting from because we have inherited from something from the collection module, and the items comes from the inheritance tree, and it will return us all the elements. And this will be in fact a generator. So with list on an iterator that refers to the generator, this returns us all the elements. I'm creating a new table, and then I have to add all my elements in there now. Something I will show you now. First, because I'm adding elements, I need to say the number of elements I have in the new table is 0. And I go through my key value pair in the old ones, and I'm adding the key value pair to myself, because I can say self on index K, or for key K, is V. What this calls is set item. So I have now implemented my hash map base. It's still not working because I have not specified how these buckets work. So bucket get item, bucket set item, bucket delete item. The code I have implemented is also available in the slides for you. And now we have the problem of collisions. I will quickly motivate the collisions, and we continue this next week. I've mentioned now the term collisions a few times, and the collision means that I have 2 keys, key 1 and key 2, that have the same hash value. Here in this case, the same index, the same bucket index. That's a collision, and this will complicate now how we can insert, search, and delete, because 2 keys may just be at the same index. And for this, I need different collision handling schemes. And there are 2 available. And Those are the ones we will discuss next week. And next week, we will implement one of these strategies, and we will also look at complexity. And we will explore next week why we picked that threshold and said that the number of elements, when the number of elements is greater than half of the capacity, that we're then resizing already. That's what we will see next week. And we will also next week study the Python dictionaries a little bit in greater detail. But probably we only need half an hour or less next week to finish the hash maps or maps and hash tables. And then we'll continue with the next chapter. Uh, Concerning the coursework, I've talked about the coursework today. We've done decision tree learning, so you're able to implement decision tree learning now, and you're able to start maybe with some of the very initial problems of the maps and hash tables, but you're able to continue with the bigger ones like 13.3 and 13.4 after next week's lecture, when we actually implement concrete collision handling schemes, for which we will implement then bucket get item, bucket set item, and bucket delete item. About next week Thursday is a public holiday, so next week Friday is something we often refer to as a bridge day. And I know a lot of professors cancel their classes on bridge days. I don't. So I'll be in the lab next week Friday from 8 to 3:30, and I'd be very happy to see you in the lab, since there's lots of work to do, like implementing your decision tree learning. Decision tree learning will be also discussed in the tutorial again by my teaching assistant in a few weeks' time. So you should definitely go to the tutorial if you want to get more hands-on practice and understand in greater detail how decision tree learning works, since this is an important topic also with regards to the coursework. In past exams, the topic of decision tree learning also pops up often. And it's not that difficult. It's just something for which you need a little bit more practice. So please go to the tutorial and talk to my teaching assistant there. And next week we continue with hash tables. Are there any questions, or if you're all good? So with there not be any questions, enjoy the open day at university today, and I'll see you next week on campus, as well as then for the lecture in the afternoon at 3:45. Take care and goodbye.